Okay. Now, the plan that we have today to work is essentially, it's a kind of a revision of what we did a couple of days ago before the weekend. And it was essentially the concept of finding actually the optimal, which is going to be the max or mean problem. Then essentially, for example, we have one functions. We said that f of x, for example, if I want to say, for example, let me find one thing from the text. For example, this function, which is 1 plus 3x to the power 2 minus 2x to the power 3. For example, imagine that this function represents the overall cost of a manufacturing plant. Then somebody asks you, for example, x, because most of the things that we have done through the IB, I should say, work was that solve the math within a context. For example, imagine that if f of x represents the overall cost of a manufacturing plant and x represents the output. For example, if you study, for example, industrial engineering, somebody may ask you at how many outputs your overall cost is either maximized, that they can think what needs to be done in order to reduce the cost, or they may ask you at what output, for example, what number of the outputs, for example, the cost is minimized, which makes you happy because when your cost is minimized, you can have higher profits. Now, for example, you can expect these kind of scenarios with the optimal finding problems that you are supposed to find the max or minimum. On the day that we worked, we essentially developed a kind of an algorithm. The first method was that the first step of that algorithm, in order to find the max or minimum of a function, essentially was this: to find critical values. Essentially, that was one of the first few things, one of the first steps that we talked about that a couple of days ago before the weekend. If that's going to be the case, and if you look at this function, which I just put as an example here, and now that we're going to find its minimum or maximum, the first step is that I find its critical value. In order to find the critical value, you have to find the derivative of the function. If the function is a single variable function, which it means that the function is built with only one variable, which is x, then the thing that we have to do first in order to find the critical value is find the derivative of the function, then equate it to 0. That's the thing that we plan to do. Now, if I'm just going to follow this step, I'm just going to solve this, say d over dx of f of x, which represents the rate of change of the function as x, its variable changes, is given based on the power rules that we have learned before. We know that based on the power rules that I'm just going to highlight it here very quickly, that d over dx of ax to the power n is anx to the power n minus 1. If that's going to be the case, then you see that the derivative of this function, the derivative of 1 becomes 0, 3 times 3x squared becomes 6x plus, no, sorry, it's going to be minus 2 times 3 becomes 6, x to the power 2. Then essentially you find the first derivative of this function represented like this. Then what needs to be done is that we say that we need to find the critical values. The critical values is given as we get the derivative of the function goes to 0. It means that the derivative of the function was 6x minus 6x squared goes to 0, which means that if we take 6x as a factor, bring it out, we are left with 1, and we are left with x over there goes to 0. Then you see very easily that if you solve this equation, either you get x to be 0, that is going to be my first critical value, and also 1 minus x becomes 0, which means that x needs to be plus 1. This other point is essentially my second critical point. Then I say that I can just put a tick mark on this step, because at the first step that I needed to find the critical value first, I find the derivative of the function, which is this. Then I solve this equation, which means that I took the derivative of function goes to 0. Then I solve for x. The zeros of this expression becomes my critical value. I got one critical value 0, and I got the second critical value as 1. Okay, now we are done the first step. And any questions so far? Everyone is fine? Nobody talks today. Okay. Now, I assume that when nobody asks a question, it means that everything is fine. Now, my first step is successfully down. I need to just start the second step. But before I do the second step, I have to remind you of one thing. And that's the thing that I just want to discuss about this. Imagine that this is the x, y axis, and that's the origin. And now I have a function which is called f of x plotted there. Now, what we talked about before the weekend was that when we find, this is very important, guys, please listen very carefully. Let me choose a line, that's it, and let me choose also this color like that. Guys, look at this. There are essentially 2 points that you can see that if you draw a tangent, let me keep working on it. Look at these 2 points. These 2 points, if you plot the tangent, it is going to be my first tangent line, and also this one, it's another tangent line to that point. If I put the tangent line for these 2 points, the point which I call this one x1, the other one I call that x2. Please listen to this part very carefully. It is very important. Look at this. These 2 points, which they are represented at x1 and x2, you see that the tangent line, which is highlighted in green, it's parallel to the x-axis. Then, if the tangent line at point x1 and x2 is parallel to the x-axis, it means what? Anybody can guess? What is the derivative of the function at these 2 points? Anybody can guess? Nobody wants to talk? Okay, I'm sure you know this. Let me just verbalize that on your behalf. Look at this. At point x1, you see that the tangent line is parallel to the x-axis. If that's parallel to the x-axis, then if we look at this, because you remember from a couple of sessions before, we said that d over dx of the function evaluated at point x0, for example, x1 here, it's essentially tangent of the alpha, alpha is the angle of the tangent line, which essentially it gives you what? It gives you A. A is slope of the tangent. And if you remember, that was a thing that when we talked about that many sessions ago, we said that this very important line connects and reconciles the analytic perspective of the derivative of a function with its geometric interpretation. Guys, hold on a second. I come back in a second. Just hold on a second. Sorry, guys, I had to open the door. Sorry. Okay, now, if you remember, we said that this very important line, piece of information, it's very important because it connects the analytic interpretation of the derivative of the functions to its geometric interpretation. Now, if I come back to the same thing that we had, we see that the tangent line is parallel to the x-axis. It means that the alpha is 0. If alpha is 0, it means that the tangent of the alpha is also 0, which then means that the slope of the tangent is 0, but ultimately means that d over dx of f of x at that particular point is 0, which it means that if you compare this conclusion that we had over here, with the thing that we did a couple of minutes ago, that on the step number 1, we find the derivative of the function, which it was here, and we solve the problem if the derivative becomes 0, and now we say that the derivative of the function at this particular point that the tangent is parallel to the x is 0, it means that the critical point that you found on step number 1 is nothing except the points that the derivative is 0 and the tangent line is parallel to the x-axis. Then, if you have a function between two intervals, then you see that the two tangent lines are parallel to the x-axis. This means that those points are your critical points. This is very important that I just wanted to emphasize on it. That's nothing new. That's something which you also learned it many sessions ago. No questions, guys, so far? Now, I just want to just move on. I'm just going to also remind you of something that we also discussed. We said that the point, which the first critical point, x1, it is essentially is standing on the top. If you imagine there is an interval which is between 0 and, for example, any point over here, you see that this point relatively to the other points of the plot is standing at the summit much higher than the others. That is the reason we call this point maximum, local maximum, or global maximum in this interval from 0 to, for example, x2. And the other point, which stands at the lowest point, here we called it minimum. Then you see that as another conclusion that the points minimum and maximum just happens at the points that the critical points is evaluated on the step number 1. Step number 1, what did we do? We said that, okay, we find the critical points, the points that the derivative of the function there is 0. Now, we say that if we find these points are targets for the max or minimum. How they can be just the actual max or minimum is this. Look at this. You see that if there is any point before the x1, if you find the tangent, it somehow is parallel to the y equals to x. The slope of a tangent is positive. At the point which is the maximum, the slope is 0, then suddenly the slope becomes negative. then it was the first thing that we learned. If the slope, it was the thing that I'm just going to write it here. If A, as I mentioned here, is the slope of the tangent, if A is positive, then suddenly A becomes negative, then it means that you got your maximum point. However, a situation like this, for example, for the x2, if the slope of a tangent before that point is negative, then it becomes positive like this. It's parallel to the y equals to x. That's why I call that the slope of that is positive. Then A becomes positive. Then it means that you got a minimum value representing that point. Now, guys, my friends, now these 2 points that we mentioned here is going to be extremely important, and as what we discussed about them before. Now, I'm just going to use whatever I have on this slide onto the next one and solve the same problem that you're trying to solve. I'm just going to the next line. I write the functions again. We said that f of x is 1 plus 3x squared minus 2 times x to the power 3. As an immediate first step, we said that d over dx of f of x is going to be 6x minus 6x squared, or you could factor it as 6x times 1 minus x. Now, and we find then as a result, we had two critical values, x1 equals to 0 and x2 equals to plus 1. The next step in our method that we covered, and also we discussed about that on the day that we talked about the max-mean problem, was that to create a kind of a sign table. Sign table is something that you also encounter that on functions level 4, advanced function. Now I'm just going to review that once more for you. In order to find, I should say, to create the signing table, what I'm going to do is that I arbitrarily draw an x-axis. On the x-axis which I have drawn, I highlight these two critical points which I have. Please take a note if the concepts from the signing table or sign table is not familiar for you, please take a note at every step which I'm doing, and also at the end, because this video is recorded, you can go back to watch this. Look at this. The first thing which I'm doing for the sign table is draw an x-axis. The second step which I'm going to do is that to indicate those two critical values, or as many as critical values which I find on the previous step on the x-axis. I found two critical values. The first critical value was 0. The other one was plus 1. When you have done this, the next step is that you simply draw a vertical line in these two critical values. Because now, by doing this, you are, I call that, intervalizing the x-axis. It means that the x-axis now, which spans from, let's say, if I want to say, it spans from minus infinity to plus infinity, then you see that by doing this, you segmentalized or intervalized your x-axis. One part of the x-axis is from minus infinity to 0. The second interval is between 0 to plus 1. And the third interval is going to be from plus 1 all the way to the infinity. And essentially, that's what I did. Then, first, draw the x-axis. Second, segmentalize your x-axis by highlighting your critical values. The next thing which I'm going to do is that I'm just going to indicate the factorized format of my function. Coincidentally, this question, it was very easy because it gave us two factors, but not necessarily every maximum problem gives you a factored format of the first derivative. Sometimes you may not get that. Then no worries, you can also work with one form of the function. Now that we have the factorized format, I take benefits from it, and I'm just going to highlight two. I'm going to highlight two factors at each row. If you have only one expression for function, you have only one entry to make. Okay, now, the first thing that you can just put here, what is that? The first item that it's going to fill my first row is going to be the first part of the function. I put 6x. And the second line is going to be the second factorized format, 1 minus x. Remember, you still can do that by 6x minus x squared without factorizing. Then you had only one horizontal column, which it was only for 6x minus x squared. And also, the last one represents the product of these two expressions, because on the last line, I make sure that I reconstruct the first function that I started with, which is 6x times 1 minus x. You see that this is exactly this function. I reconstructed it. Now that's the time. Then I recap. First, draw the x-axis. Second, segmentalize your x-axis by pinpointing your critical values taken from the previous step. Third step, highlight the p parts of your functions, the derivative function, not the exact function. Look at this 6x times 1 minus x is your derivative functions, not the actual functions. Then reconstruct the function on these lines. It was step number 3. Step number 4, which is actually my favorite part, is this. I'm just going to play with the signs. Look at this. Here is minus infinity to 0, from 0 to plus 1, from plus 1 to plus infinity. I randomly pick up a number and put that inside each function to see what is the sign of that value. Imagine between 0 and minus infinity, there are infinite choices that you can make. But I go with the easiest one. I say that minus 1, for example. Minus 1 is something between here. For example, minus 1. I put minus 1 into 6x, becomes minus 6. Then I infer that the sign in this cell of the table is going to be minus. Now, what else I'm going to do is this. Let me see, I have a question. Okay. Now, I also do the same thing over the column. I put now minus 1, I take it, bring it into the second function. Put minus 1 there, becomes 1 minus minus 1 becomes how much? Becomes plus. Then I infer that any number between this interval, which is segments of between 0 and minus infinity, it becomes plus. Imagine you put plus minus 4 also in that interval. Becomes 1 minus minus 4, which becomes 1 plus 4 becomes plus 5. Then only with one number as a sample in that interval, I make a huge conclusion that every other numbers, it gives a positive number. Then as a result, the reconstructed function, which is 6x times 1 minus x, is the product of these two signs. Minus times plus gives you what? Gives you minus. That's what I look for. Now, I go to the next interval. The next interval is between 0 to plus 1. I select a random number, for example, 0.5. Any random number, which is going to be easy to work with. If I put 0.5 into the first function, it becomes 6 times 0.5, which is positive 3. We do not check the magnitude of the number, but as long as this is positive, that's all that we care about, which it means that it is a positive in this interval. The same thing, I put 0.5 into the second function, which is this, becomes 1 minus 0.5, which it gives you what? Which it gives you, again, 0.5, which it means that this is, again, is going to be positive. Means 1 minus 0.5, it gives you 0.5 plus, which means a plus 1. Then you see that the reconstructed function is the product of these two signs. You got positive times positive, it gives you what? It gives you positive. Now, we are almost getting towards the end. Look at this. Also, we had another interval, which it was from +1 all the way to the plus infinity. I randomly pick up a number. The number I pick up is going to be, let's say, for example, I pick up this number between +1 and infinity. I randomly select +2. It's easy to work with that. I substitute +2 on the first line, 6x. I get 6 times 2 becomes +12. Because it gives you a positive number, then I make an inference that it has to be a plus value there. Now, I do the same thing. I put +2 inside the second factor of that expression. 1 minus +2. 1 minus +2 becomes how much? 1 minus 2 gives you -1, which it means that it has to be a negative number. You see that only one number, which is selected randomly between +1 and plus infinity, it gives you the cool conclusion that you're looking for. For example, you choose +10, still you have 1 minus 10 is -9. It is still negative. Now, as a final conclusion, the product of these two, plus times minus, it gives you a minus number. Then I got the expression of my derivative, 6x times 1 minus x. Now, look at this one. Look at this step. It's like going to the art class. Why I call this the art class? Because we are going to draw some lines, some interesting lines. Look at this. The value here is negative. What is negative? It's the sign of the derivative of the function. It is the sign of the derivative of the function. If the sign is negative, it means that the slope is negative. What kind of function had the negative slope? It was the function which it was decreasing like this. However, this one is positive. It means that 6x times 1 minus x, which is the derivative of the function, which represents the slope of the tangent line, is positive. What kind of functions they have positive slopes? They have this shape. The slope is positive. In order to memorize it, always look at the quadratic function like that, with this shape. You cut this in half, like the apple. You cut the apple in half. The left one, as you can see, it gives you negative slope. The right half, it gives you the positive slope. Then that's how you can remember the shape of these drawings. And also for the last interval, you see that here, the slope of the tangent is negative, which it means that it can be represented by this line. Now, any questions, guys, so far? Everything is fine? Please, if you are shy to speak, put your questions on the Google, on the chat room. Now you're almost 2 seconds away to finalize this problem. And what is that 2 seconds away is this. Now we come to connect these parts. Look at this. Do you remember from the thing that we discussed here? We said that if the slope is positive, then suddenly becomes negative. We have the maximum like this. Sorry, look at this. The slope is negative, suddenly becomes positive. Sorry, the slope is positive. The slope is positive, suddenly becomes negative. Then this critical point becomes a maximum. But now look at the other one. We said that the slope is negative, suddenly becomes positive, then this point becomes the minimum point. Now, I'm just going to use the same concept. The slope is negative, suddenly becomes positive. You connect these two pieces together, you get the same thing. Then it means that this point represents the minimum. What was this point? Was point which is 0. Then point 0 is a minimum. Now look at this one. You have then between the interval from minus infinity to 0, you got 0 as a minimum point. Now look at this one. From 0 to all the way to the plus infinity, you get the slope, which is positive, suddenly becomes negative. Look at this. The slope is positive, suddenly becomes negative, which it means that this point, it represents a maximum point. What is this point? This is +1. Then as a result, I conclude that I got 2 results. The first result is that my first critical point, which was x equal to 0, it represents what? It represents the minimum point. However, the second critical point, which it was +1, should represent the maximum value. Why? Because I come back, see that the slope is negative, suddenly becomes positive. Look at this. Then it represents the minimum point. Now over here, the slope is positive, suddenly becomes negative. Then it means that the sudden change results in the point to be the maximum. Now I wrote the conclusion here. And essentially we are done. Then before we take our 1-minute break, I'm just going to summarize what we did. What we did was this. They had this polynomial, they were looking for max minimum. The first step was to find the critical values. What are the critical values? They are the roots of the derivative of the function. We find it as 0 and 1. The second thing was that, remember this one. We said that these critical values are the points essentially that the tangent is parallel to the x-axis. However, we noticed that if the slope is positive, suddenly becomes negative, it represents the max. The reverse case is that if the slope is negative, suddenly becomes positive, it represents the minimum. Then as a result, I constructed the sign of table, the table sign, and I put the x-axis. I intervalized with the critical values the x-axis. I represented the part of the derivative of the functions here. I reconstructed it, then randomly selected one point from each interval and decided on its sign. Then I find the product of it. Then the sudden changes of the slope from minus to positive represents the minimum. The positive to negative represents the maximum. There is one thing that we also need to do. We call that the second derivative test. It's a very interesting thing. I think we can talk about that. It's essentially kind of a test. Normally we use that in order to make sure that we didn't do any problems. We didn't do any mistakes. It becomes a kind of a test to check our work. I'm going to talk about that after the break. We're going to take, what time is it now? 8, almost 10. We take a minute or 2 minutes break that you can just rework the case that you had. Then when we come back, I'm going to talk about the second derivative test. Do you have any questions before we leave for the break? Let me see. One question showed up. This somebody says that we do not need the second derivative for the test. You do not need that, but it becomes part of the curriculum that you need to learn for the IB tests. I'm just gonna very quickly say that because you need to find the second derivative for the test tomorrow, oh no, for the day after, but I teach you the second derivative, but you can use it if you want in order to double check your work, in order to make sure that you didn't just do any mistake. But of course, for the test, you need to know how to get the second derivative of your function. That was a good point. Thank you very much. Thank you very much, Elizabeth. Now, guys, it's now 8:11. Please take a 2 minutes break. You can just review the thing that we need. Come back by 8:13. Then we continue with some cooler stuff. Okay. Awesome. Welcome back. I hope that you enjoyed your long break. 2 minutes break. Now, guys, any question before we continue our work? Let me see. Awesome. Awesome. Thanks, Gabriel. Now, look at this. Now, I want to introduce to you, if somehow it's a new concept to some of you. However, I'm just going to stop for this problem. We said that our minimum is the point x equal to 0, and the maximum happens at the x equal to 1. However, somebody may ask you, okay, if the function that we worked, and we talked about this, for example, we give it a kind of a context that 1 plus 3x squared minus 2x to the power 3. Somebody may ask you, give it some interpretation. We said that the f of x is the overall cost to manufacture, for example, a book, and x is the number of the outputs. Outputs can be anything, a book that you produced, you manufactured a shoe or anything. Now, then it means that it's very easy to see that it's not a realistic case, but somehow it means that your cost is minimum if you haven't produced anything. Look at this. Oh, it's obvious. Then you haven't produced, manufactured anything. You haven't incurred any manufacturing costs, which it means that your cost is minimized. However, if you put it to the function itself, means f of x equal to 0, it becomes 1. Then what is this? We expect not to have any cost. We call that kind of an intercept. Everyone knows that. It can be, for example, the cost of the utilities of your manufacturing. And you see that after producing the first item, your manufacturing cost is maximized. Although the context that we give to that function is not realistic, but it's a very funny one. It means that you produce one item and your cost is maximized. Oh, that's so funny. But how much is that cost? It means that the f of x equal to 1, which you put 1 in the actual function itself, which becomes 1 plus 3 times 1 to the power 2 minus 2 times 1 to the power 3. It becomes 1 plus 3 minus 2 becomes 2. Then it means that your maximum cost is 2, for example, 2 pounds, $2. Then the minimum point happens at x equal to 0 and y equals to 1. The maximum happens at x equal to 1 and y equals to 2. That's essentially what we did if, for example, the max minimum, because normally in the later chapters of the book, as we are working, it's insane. We start to look at the function, say that, find the maximum and minimum. You ask yourself for what? And if you find the maximum or minimum, you ask, so what? Then you have to give a context to that. You have, for example, a manufacturing plants. X represents your output, f of x is your overall costs. And it was one example. You can find an infinite number of the examples. Now, I'm just going to leave this question here for just a second. Now go to the second, I should say importantly, that I'm just going to talk. It is going to be absolutely important for also the test on November the 3rd. I'm just starting again with the same function. I say that, okay, the function that we work, it was 1 plus 3x squared minus 2x to the power 3. Now, we look into that. The first item that we did, we said that d over dx of f of x is going to be 6x minus 6x squared. And what was the key formula for this? What it was essentially the power rule, which it said that the derivative of any power function is just this. Now, and ask yourself, the derivative that you got this is still a function by itself. By nature, the derivative of your function itself is a function. Then you ask yourself, is it possible to again take the derivative using the same power rule from the derivative of this function? What do I mean? I mean this. Can I start from here and say d over dx of f of x? Can I do that? Then you say, wait a minute. I keep d over dx outside, and instead of d of dx of f of x, I write its equivalent from the upper line, which is 6x minus 6x squared. That's what we think, and that's what we plan to do. So far, it's so obvious. You say that the first derivative, d over dx of f of x, is given at the prior step. Then I'm just going to act this, I should say, this operator as a hammer into each one term, again using the same power rule, which it gives you what? It gives you d over dx of 6x minus d over dx of 6x squared. I use the power rule, and I notice that between these two power functions, I have the minus sign. Then eventually the things becomes absolutely easy. The derivative of the 6x becomes 6, still using the power rules, minus derivative of 6x squared becomes minus 12x. Interesting thing, which I can conclude that as a result, d over dx of d over dx of f of x, I'm just going to write it symbolically as d2 over dx2 of f of x. This is nothing except the fact that we did and this is represented by a new notations, by a new symbol. Means d to the, it's not the power, it's not an exponent. It means that the functions that you are given, which is f of x, you take derivative twice from it. And that 2 over here, that's the language which indicates to you take derivative twice from that expression. If you do this from the thing that we did, it becomes what? I'm just going to write it here. It becomes the expression that we got here, 6 minus 12x. That's essentially is the second derivative concepts that we talked about this. Okay, any questions, guys, on this? It's somehow a little bit something new, but everyone is fine with this? Okay, means silence means hopefully yes, everyone is fine. Awesome. Thank you, Gabriel. Thank you. Now, guys, you may ask yourself, is it insane? Isn't that insane that we are talking about the max mean problem? We have, for example, we have a manufacturing facility. We are looking to see what is the output that it brings our costs to a maximum or brings our costs in our manufacturing plants to a minimum. Then suddenly the teacher starts to talk about the second derivative out of nowhere on Monday evening. Am I crazy or what? But my friends, I'm going to tell you, give me 1 minute. I'm just going to show you how relevant is that going to be. We said that with the same functions that we had, the second derivative of the functions that we introduced, that it was 1 plus 3x squared minus 2 times x to the power 3, as we found here, is 6 minus 12x. Six minus 12x. Now, the thing which I just want to say is this. If I take the second derivative, bring it back to the same problem of the maximum minimum which I had here. And I say the second derivative, I'm not going to withdraw this. I'm going to very briefly highlight this here. The next session, when we meet in the class, we are just going to solve more problems. I'm just going to look into these two max and minimum values which I found. I say that I found that at x equal to 0, it represented my minimum, which it means that if I look into that as a proxy graph, I call this, the function represents like this. And this point, x equal to 0, which it gets a horizontal tangent at 0, it becomes my minimum point. But I say that, wait a minute, how can I relate this one to the second derivative? I say that when we are working with these kind of problems, and when we just find the second derivative, and if we just put the second derivative, I'm just going to say this as a theorem. We're going to talk about that more in the class on the next session that we are going to meet, but it doesn't hurt to talk about this now. I say that if I have d, if I say, for example, d over dx of x naught is 0, which it means that this point is my critical point. And if I can show that d2 of dx2 of that critical point is positive, then I conclude that x0 is a minimum point. This is my test. It calls that concave up. I'm going to talk more about that next session that we meet. However, with the second point that I'm just going to talk is that if, again, the first derivative of my critical point is 0 and the second derivative of that point critical value, it gives you a negative number, it means that x0 is a maximum. They call that concave down. You can use it as a test. We set x equal to 0 based on what we did here. It becomes a minimum value. Let's use this test using the second derivative. We say that, okay, now look at this. The second derivative of x0, it's what? It's 6 minus 12x evaluated at x equal to 0. Becomes, you put 0 there. Oh, no, sorry. Just, I had to. I mean 1 plus 3x squared minus 2x cubed at x evaluated at 0 is essentially 6 minus 12x evaluated at 0, which becomes 6. You put 0 to the x, get 6 minus 12 times 0, you get 6, which is a positive number. Our test says that if you have a critical value, 0 was a critical value. The second derivative evaluated at the critical value becomes positive. Then that point for sure is a minimum point. Then we got the positive number and it confirms that x equal to 0 is negative. Now, we go back also to the point x equal to 1. We got this couple of minutes ago through our sign table that x equal to 1 is a minimum point. X equal to 1 is a maximum point. Then let's see with the second derivative test. We got it, its maximum point. It means that if you have it like that, 0.1, it's the maximum point and is concaving down. I do the second derivative test. The second derivative test means what? I get d over dx squared of 1 plus 3x squared minus 2x cubed. This is also cube here. Evaluated at 1 is 6 minus 12x. Evaluated at is equal to 1 becomes 6 minus 12, which is minus 6, and this is negative. It confirms also to the second derivative test. Means that if your critical point, which derivative, the first derivative is 0, and you find your critical point, the second derivative evaluated at that critical point x0 is something negative, the function is concave down, it's looking down like this. And that point becomes your maximum point. And because now the second derivative evaluated at 1, it's minus, it gives us essentially, it confirms that x equal to 1 is a maximum point. That's essentially the new lesson that we had today. We are not going to have that extensive applications of the second derivative on the test, but we need that for the IB program. But also during the class session, we are going to talk more about this as it is Incredibly important concept. Now, I know that it's a little bit too much, but no worries. You do not have these tests for the second test that we talked on your test on November the 3rd. But all that you need to know is that from the function, you can get derivative twice. And that's the thing which matters at this stage. The second derivative, it's not that much important. Okay. Any questions, guys? Okay, let's see the first question. Oh, I'm so impressed. Nobody has a question. It means that either the content is too easy, or you people are super smart, or I'm a good teacher. Oh, maybe all of them. Maybe all of them at the same time. Now, let's see. We have almost, for if we assume that we are running a normal class, we have almost 10 minutes before the end of the class. Let's see, and nobody has a question with that regard. Let me see. Then I'm just gonna give you guys one question. It was from, I should say, the handout, which I gave it to you. I recommend to look into that, possibly tonight. I give you also the homework, if you remember the handouts that you have on page number 178, and the handouts that you have, equation number 1, 2, and 3, and 1 and 2 and 3, essentially it was the main homework that I gave that to you. But also, I'm just going to give you one. You look into that for tonight. And essentially that's this: to find the max or minimum for a function which is given like this. You get y equals to 4 minus 3x squared minus x to the power 4. I just wanted to ask you, please follow exactly the same thing that we did today, step by step, all the things that we covered today, to find either the maximum or minimum of this function. You know that as what we did, essentially you have to find first the critical value, then construct the table of sign, then find the max minimum based on the concepts that we introduced here and reviewed it today. It was not a new one. And also, I recommend you at the end, go back to just use the second derivative test in order to check if the max or minimum that you obtained from, I should say, the table of sign before confirms exactly with the same thing that you obtained before. Okay, I think that's going to be pretty much of the lesson for today. You see, the Zoom session makes the sessions more productive. We can talk more and more and more and teach more there. Okay, now before we finish the session today, let me stop at this slide. This is going to be the thing that I hope that you do this right away after this session. It consolidates the things that you learn. I'm just going to put a recording of the session in the next 5 minutes on the Google Classroom. Please make sure that to watch it in case if you have any questions. Guys, before we finish the session, I wonder if anybody has a question, otherwise we end the session today. No questions on the chat? If no, guys, I just wanted to thank you very much for just coming to the class, and my apologies that I just put the session at this very late hour. Thank you very much. I'm just going to put a recording in the next 15 minutes, I should say, on the Google Classroom. Make sure that to watch it. And also, please solve the same equation which I put for you using the same steps that we did on the previous example. Okay, thank you also to you guys. Thank you, Brooke. Thank you, Gabriel. And see you all the next session. Have a very good night and see you guys later then. Thank you also, Tommy. Thank you, Caitlin. And guys, make sure that you have a wonderful night then. See you all tomorrow. Take good care, everyone. Just gonna stop the share. Let me save it.